This video is about Hippocrates' most famous accomplishment, known as the Quadrature of the Lune. First of all, what is a lune? A lune is the shape that you get by taking a circle and another circle. And basically, what I'm imagining is that I'm taking the green circle and I'm cutting away everything that's in the red circle. And then what's left over is shaded in green. So basically, it looks like the shape of a crescent moon. Now, the problem that Hippocrates was trying to figure out is how to use a compass and a straight edge to construct a square with the same area as a given circle. He wasn't able to solve that problem, but he was able to solve the problem when the shape is a part of the circle, namely the lune. So the first thing to note is that he built his lune on a 45, 45, 90 triangle. And so that means that this angle up here is 90 degrees, and these two base angles are 45 degrees. That means that this is an isosceles triangle. And so how did he draw his lune? So the first thing he does is he draws a semicircle on one of the legs of the right triangle. So that's the semicircle. That here's the diameter of the semicircle, and then here's the rounded part of the semicircle. Next, he drew a circle that was centered at the midpoint of the hypotenuse. And then what's the radius of the circle? It's the distance from the hypotenuse of the triangle to the opposite vertex of the triangle. So this is a semicircle centered at the midpoint of segment AB, and the radius of the circle is basically OA, OC, or OB. So all of those are the radius of the semicircle. So basically he takes the little circle and subtracts the big circle, and then what's left is shaded in dark gray, and that is the lune that Hippocrates was squaring. Now, the claim is, so what exactly did he prove? So this lune, which we're going to call L, has area equal to the area of this green triangle. So basically, this green triangle is half of the triangle that we started with. So the gray lune has the same area as the green triangle. And then we're going to use the fact that we know how to square a triangle. And since we can square a triangle, in other words, we can draw a square with the same area as the triangle. So the square will have the same area as this triangle, and this triangle has the same area as this lune. Therefore, this square has the same area as this lune. By the way, because this is a 45, 45, 90 triangle, there's a very easy way to square it. So here it is down here. Let's cut this triangle exactly in half. And then we're going to rearrange the two pieces. So the blue piece is going to go down here. The yellow piece is going to go up here. And because these angles are 45 degrees, when you add up 45 and 45, you get 90 degrees. These angles were already 90 degrees. So the bottom line is that all of these are 90 degrees. And because of the fact that this length and this length are the same, because they're both this length right here, it's a square. Here is the theorem. The lune L has area equal to triangle ACO. So it's the triangle that we previously colored in green. So here is our proof. So we start with semicircles on the right triangle. So here's so basically here's our right triangle right here. So this is our right angle. And then these other angles are 45 degrees. We're going to draw semicircles on all of the sides of the triangle. So here's a semicircle, here's a semicircle, and here's a semicircle. So we're going to call these areas U, V, and W. Now at this point, we need to recall that Hippocrates had a generalization of the Pythagorean theorem. He said that you can draw any shape at all on the three sides of a right triangle, as long as the shapes are similar. And so the easiest way to think about what does it mean for the shapes to be similar, you can transform one into the other by just like magnifying it or shrinking it. So U and V are actually exactly the same. They're the same semicircle because since this is an isosceles triangle, these lengths are the same, and therefore these semicircles are exactly the same. So those figures are congruent, and congruent figures are always similar. But notice that we have a semicircle on the hypotenuse as well. Well, this semicircle looks exactly the same as that semicircle. It's just magnified. So basically, it's like taking the small semicircle and then blowing it up to make it bigger, like using a magnifying glass, just make it look bigger without changing the shape. And then we're going to put it on the hypotenuse. So these three shapes are similar. And so according to Hippocrates, so just like Pythagoras said, if these were squares, we would have said A plus B equals C. That was what Pythagoras said, but he used squares. But Hippocrates said, you know what, any shape works. So I'm going to do something that's not a square. I'm going to do a semicircle. So we have the same theorem, U plus V equals W. So that's Hippocrates' generalization of the Pythagorean theorem. So now let's look at the rest of the proof. So let me just I want to be able to see this little drawing. So since this is an isosceles triangle, this length and this length are the same. So segment AC is congruent to segment CB, meaning they have the same length. And so that means that this semicircle is congruent to this semicircle, and therefore they must have the same area because they're exactly the same shape. So now I'm going to take this equation right here, U plus V equals W, and since V is equal to U, I'm going to make a substitution. So this V is going to become a U. So now I get U plus U is equal to W. Okay, so now here's the trick. The trick is, this was our original picture over here. So we had a semicircle on all of the sides of the right triangle. And basically, we're going to imagine that this semicircle down here, we're going to flip it up. So instead of looking at a semicircle under the hypotenuse, we're going to look at the semicircle above the hypotenuse. And so now our picture looks like this. And the lune that we're interested in is this region right here. So now let's let T be the area of the triangle. Let S be the total area of the whole figure, like everything. So if you color in everything, that's what we're calling S. And so that's what's illustrated over here. So basically, it kind of looks like the shape of a Mickey Mouse hat, you know, with Mickey Mouse ears. So that's the shape that we're calling S. Now notice that there are two different ways of breaking up the shape S into smaller pieces. One way of breaking up that shape is here, where you have the triangle and then the two semicircles. But here's another way. Here's the circle W. Remember, W was the semicircle that we started with. It was drawn under the hypotenuse. Now the same semicircle is drawn above the hypotenuse. It's the same semicircle, and so the area is still the same. So that still has area W, and then we're calling the area of the lune L. So if you add up all these regions, it's going to add up to S. And this is exactly the same shape. So if you add up all those regions, it's also going to add up to S. So therefore, these two shapes are just different ways of dividing this shape up into smaller pieces. And so we have, from this part, we have L plus W. That's what we wrote right here. And then looking at it where we broke it up into pieces in a different way, we have U plus T, and that's here. So L plus W equals U plus T. But remember, we said that U plus U is equal to W. So we're going to make that substitution right here. So that U plus U is going to become a W. And so now, again, looking at this equation and making that substitution, we get L plus W is equal to U plus U is W plus T. So we have L plus W is equal to W plus T. We see that we have a W on both sides of this equation. So let's go ahead and subtract W from both sides. So this side becomes 2 times L. This side is just T. So we get 2L is equal to T. Thus, L is 1/2 of T. So that means that the area of this lune is 1/2 of the area of this. So basically we need to cut that in half, and then half of that triangle. So L is equal to 1/2 of T. So thus L has area equal to the area of triangle ACO. And then if you go back to our original picture, ACO. So that was half of our original triangle.